Here we can see a demonstration of the 1-bit magnitude comparator on a breadboard showing all 4 inputs. Now on a PCB we can see all 4 inputs plus the displayed values. Now into the parts. 1 logic AND gate, 1 logic NOT gate, and 1 logic NOR gate. 1 4-pin LED, 2 switches, and 3 resistors, 2 470 and 1 10K. In the math world, we use base 10 to control all the inputs. As we can see up here, we're using base 10, while in the binary world, we use base 2, which uses just zeros and ones. These two numbers are equal, just in different bases. In base 10, we use symbols like this to configure our inputs, while in base 2, we use symbols like this to configure inputs. Now that we understand how inputs can be configured, let's look at the 1-bit comparator. Now that we have an understanding of how inputs can be configured, let's look at the 2-bit comparator. As we can see here, we have 2 switches to start off. The 2 switches can either be going directly to ground or through the circuit. This represents how a switch can give us the inputs 0 or 1, which gives us the binary system. Now let's look at what happens if you give either switch an input of 1. Let's give both A and B an input of 1 and see what happens. When both inputs are given an input of 1, they go through the NOT gate, which turns them both to 0 because of how NOT gate functions, which means that an AND gate, based on how it functions, will also produce a 0. And when both these AND gates have produced a 0, it will then flow to the NOR gate, because the only input that gives a NOR gate an input of 1 is an input of 0, turning on the green LED. Here shows all 4 possible outcomes for when you use the 1-bit magnitude comparator. As we can see, the 4 possible outcomes are green, blue, red, and green.